All right, today we're looking at 7-6, you guys. Pretty straightforward as things go. We've already talked about how a lot of logarithms are log base 10. The button on our calculator that says log, L-O-G, that's assuming the base is 10, okay? So today, a lot of the stuff is just gonna be focused on this common logarithm and using our calculators, all right? So first things first, how to type logs into our calculator. Most of us have actually already done this because we threw some problems on the worksheet. But if you want to do log 15, all you have to do is go to your calculator, type in log 15. You don't have to type in log base 10, okay? Your calculator, every time you hit that log key, assumes you're referring to base 10, all right? So log base 10 or 15 or log 15 should be 1.1761, okay? We're approximating the nearest 10,000. This is 4 spots over. Same thing, next question, log 340. So I hit the log button, type in 340 and enter. All right, 2.5315 should be your answer. Keep in mind, you can always check if you want this answer, remember base, power, answer. So 10 to the 1.1761 should be about 15. 10 to the 2.5315 should be about 340, okay? You can check, you don't need to. All right, so that's typing in logs. Make sure, number one, you type it correctly. Number two, you round correctly. All right. Looking at example 2, looking at base 10 in terms of earthquakes and how we use the logarithmic scale to look at energy and amplitude, essentially, okay? Earthquakes, as you can imagine, super large amounts of energy. That's why I use a logarithmic scale to kind of help denote things. If you think about a log graph, kind of looks like this, correct? So as we move this way, it still increases, but it's not as far. So we use these logarithmic scales so we can kind of condense that information so it doesn't skyrocket up like an exponential graph. All right. So kind of looking at things, we're going to use this equation to find the amount of energy released by the 2004 Sumatra earthquake, which measured 9.0 on the Richter scale and later led to the tsunami in the Philippines, I believe. All right. I actually watched a special on that this summer. Insane. Or no, it was a Dateline actually on the tsunami. Crazy. Absolutely crazy and insane. So where is the 9.0 going to go? Okay, hopefully you're realizing that it goes in for your magnitude. 1.15 times magnitude is 9.0. And we are trying to find the amount of energy. Well, so log of E equals 11.8, 1.5 times 9. This side is going to be 25.3. So the question is, what's the amount of energy? Well, remember, this is base 10, correct? So I know that 10 to the 25.3 equals E, which is the amount of energy, right? This is 1.995 times 10 to the 25th in scientific notation. Just a massive amount of energy that led to this, okay? Which is why the tsunami was probably so devastating, okay? Massive amount of energy, all right? Next question we're going on to, solving, all right? So kind of looking at this process, we're going to relate it to properties yesterday, right? We're trying to solve for x right now, and I don't know log base 6 of 86. That button does not exist on my calculator. When I type in log, it assumes base 10, okay? So what we can do is actually use our properties, okay? If I log both sides, it's going to keep my equation balanced, which is perfect. Now, on this side, If you recall from yesterday, when we have a power or log of a power, that exponent can drop up front. So we have x times log of 6. And over here we have log of 86. Notice I didn't denote any base of my logarithm. All right. If we assume it's base 10, I can use my calculator now. And to solve this, I'm just going to divide by log of 6. Divide both sides by log of 6. I can use my calculator to approximate. So I do log of 86, or log base 10 of 86, enter, divided by log base 10 of 6. Enter. Use my calculator for that. And now I get 2.486 is 0. Rounded to the nearest 10,000. Okay? Notice. Okay? This is how we solved this expression, correct? If I write this as a logarithm, this is the same as log base 6 of 86 equals x. All right? So if I transferred this exponent, I just circled in green, to logarithmic form, it's log base 6 of 86 equals x. These two mean the exact same thing. Okay? So notice the one in blue on the left, I used base 10 to solve. I was able to transfer to base 10. I was able to use my calculator. Okay? It's the same thing as the expression log base 6 of 86. That leads us into what's called the change of base theorem. Okay? And I actually kind of just went through this. If we log both sides, we wind up with x times log of a equals log of n, which means x is log of n over log of a. Keep in mind, I said we want to log both sides using base 10 because base 10 is on my calculator. There is another logarithm I could have used on my calculator, and that's the natural log. So if you did the natural log of a on both sides, you would still get the same answer. Okay? And this is where that change of base theorem kind of comes into play. All right? I know a lot of you have that fancier TI 84 color edition CE blah 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 blah. All right, there are programs on there which allow you to change base. This is what the program is actually doing. All right, basically the minds at TI wrote a program to use this change of base formula, so you don't always have to use base 10. Okay, I personally think it's important to know that you can use base 10 in logarithms, because you're not always going to have that fancier calculator. If you only have a scientific calculator, it's only programmed typically for log base 10 or natural log. Okay, so it's important to know how to use those and solve. So looking at this case, I don't want you to type this in your calculator, even though some of you have that functionality. Not everybody does. There are two other ways to solve this problem. Okay, and it's using this change of base formula. Remember, n and a. Whatever we're logging goes on top with the new base. Whatever the old base was goes on the bottom with our new base. All right, the two ways we can do this. I can use log base 10. Remember, what we're logging goes on top. Log of the old base goes on the bottom. Or I can use natural logarithm. All right. I want you to type both of these into your calculator and show that they are indeed the exact same answer. So we have log base 10 of 20 over log base 10 of 4, natural log of 20 over natural log of 4. They should give you the exact same result each time, which is 2.1610. Okay? I cannot stress enough, this is super important. Being able to change a logarithm base to anything you want, okay? You could potentially see questions about this in the future. So I want you to not rely on that program, okay? especially if this was like a no calculator question. I said, can you approximate this using a different base? So you can't use base 4, which means you can't use your calculator to solve. Can you approximate it and come up with these two expressions? Okay. So be very mindful of that going forward. Base 10 and logs are really straightforward. But yeah, 7-6, there's a short book assignment and worksheet. Make sure you work through the process. If you have any questions, let me know via discussion feed or the Google Meets. Otherwise, enjoy your day.